Hello everybody. Today it's a great pleasure to have Shira Tanny from the Institute for Advanced Study in Princeton, and she will talk about Gromov-Witten theory and the closing lemma.
Thank you, everyone. It's really a pleasure to be in the Zoominar. Right, so I will talk about this kind of a dynamical question called the closing lemma and some way to study it using holomorphic curves, and in particular a connection to Gromov-Witten theory. Okay, so everything I say today is joint with Julian Chaidez, and I wrote in advance kind of the first part of the first two boards, basically the intro. Okay, so here, this box is basically summarizing the structure of the talk. So I'll start by describing this dynamical question, which is called the closing lemma. Then I'll try to be kind of brief about it, but if you want to know more, just stop me. And then I will talk about a new class of invariants that we constructed. We call those SFT spectral gaps. They are invariants of symplectic cobordisms, and well, the name is basically SFT because they're with SFT like holomorphic curves, and spectral gaps. Well, you can think of them as kind of elements in a different set of the spectrum, but I'll say more later. And then finally, kind of towards the end, I will try to explain on an example how you can use Gromov-Witten invariants to compute these new class of invariants. Okay. All right, so let me start by describing the motivating dynamical question. This was originally asked by Poincaré, and it's quite a simple question. It goes as follows. Suppose that you have a closed symplectic manifold, and you have a Hamiltonian diffeomorphism. So this is just a diffeomorphism that is generated as the time one map of some Hamiltonian, and you have an open set. The question is basically, can you perturb the Hamiltonian diffeomorphism to have a periodic point in the open set that you chose? So here is an illustration. Suppose this is your open set. You take some generic point in the open set. Poincaré recurrence theorem tells us that if we apply phi many, many times, at some point we will come back arbitrarily close to X. So we have these almost closed orbits all around the manifold. And then the question is, can we perturb the diffeomorphism phi to get an actual closed orbit here? Okay. You can ask the same question or an analogous question in the context of Reb flows on contact manifolds. So suppose you have an odd dimensional manifold with a contact form. So that means that alpha wedge d alpha to the n minus 1 is positive. Such a contact form generates a flow via the vector field that spans kernel of d alpha and normalized such that alpha of it is 1. And you can fix an open set in your manifold, and you can ask, okay, we have again this kind of recurrence phenomena that orbits are kind of almost closing up, and you can ask, can I perturb the flow or equivalently perturb alpha so that I will have an actual, actual closed orbit here. So turn this into a loop. Okay, is the question clear? All right, so what is known about this question? Basically, in the 60s to the 80s, Pugh and Pugh-Robinson showed that this is highly doable when you allow for C1 perturbations of the vector field generating the dynamics. And these results were given the name closing lemmas. Then people were trying to figure out what happens with CK perturbations for k larger than 1. So in 91, Erman gave a counterexample, or rather a class of counterexamples, showing you that you cannot achieve, you cannot in general close such almost closed orbits with C infinity perturbations, or it was even CK for k large enough. And his examples live in any dimension starting from 4 and up. Okay, and finally, the last item in this list is a very surprising result by Erie, who showed that you can always, on contact manifolds in dimension 3, you can always close up orbits of Reb flows with C infinity small perturbations. After this work, there was a kind of a sequence of other works proving the analogous statement for Hamiltonian diffeomorphisms in dimension 2. So again, you can always perturb your flow in a C-infinity manner to produce closed orbits. Now, these results were given the name strong closing lemmas, and a part of the reason is that they actually show something stronger than just a C-infinity closing lemma. So to tell you exactly what they show, I need to give a definition. So this is a definition, and it's due to Erie. So you say that a Hamiltonian diffeomorphism satisfies or has the strong closing property if basically for every deformation that you do for the flow, so for any not completely zero H, now H is a Hamiltonian deforming your Hamiltonian flow, and it needs to be non-negative. There exists a time as you raise this deformation. I'm going to explain on the picture in a second, such that the flow perturbed by H at this time. So if you compose phi, the time one map of tau H on phi, this has a periodic point in the support of H. Okay, so let me show this on the picture. So at time 0, tau equals 0, you have no perturbation, you're with the original phi, and then you have this kind of almost closed orbit, something like this. And then you start raising this bump. And then at the property that you want to define is that at some point you have to, whatever deformation, whatever bump you chose, at some point there will be a periodic orbit passing through the support. So you necessarily, kind of any deformation creates periodic orbits. Not necessarily at the end time, but kind of between 0 and 1. This is stronger than just C-infinity closing because it tells you that if you want to produce periodic orbits through an open set, it's enough to change the flow only inside the open set. And it also tells you that basically kind of whatever deformation you do, you're going to create periodic points or periodic orbits. There's an analogous definition in the flow case, but I'm not going to repeat it. Okay, so basically these results, Erie and the following works in dimension 2 and 3, they showed that rate flows and Hamiltonian diffeomorphisms all have the strong closing property. Okay. So after these works, there were basically no examples of any rate flows or Hamiltonian diffeomorphisms that satisfy this strong closing property in higher dimensions. And then in 2021, Erie conjectured basically that this strong closing property holds for the simplest case of Reb flows that you can imagine, or that I can imagine, which are Reb flows on ellipsoids. So basically you have some natural Reb flow on the boundary of an ellipsoid. It's given by rotations of the different C factors in Cn with different speeds. And then the conjecture is that whatever bump you raise on this ellipsoid, as you raise it, at some point, a periodic orbit will be created. Okay. By now, this conjecture has 3 different proofs. So the first one was in a joint work with Chaidez, Detta, and Prasad. We used contact homology algebra. So I should say here that these results in dimension 2 and 3 were obtained using embedded contact homology. So embedded contact homology lives in dimension 3, and it has an analog called periodic flow homology in dimension 2. And kind of our motivation to use contact homology was that you can think of it as kind of a not as powerful analog in higher dimensions. So it's another homology theory that is kind of harder to work with, but it's natural to try to use it. So using that, we managed to prove this strong closing for ellipsoids and a little more than that. And then shortly after, Jinxin Xu had a very nice dynamical proof using KM normal form. And Sinelli and Sefadini managed to prove the closing property for some Hamiltonian diffeomorphisms using Hamiltonian flow homology and deduced this claim for Rev flows on ellipsoids. All right. Any questions so far? Right. So basically, after these works and like after our work and learning of the other works, we were trying to understand how we can extend the class of flows or diffeomorphisms for which this strong closing property holds, and how can we understand where the line goes between these positive results and Erman's counterexample. Basically, each one of these different proofs shows the strong closing property for more than just Rev flows on ellipsoids, but kind of they all extend in different directions. So there isn't kind of a containment of the results, right? We also couldn't come up with any way to use these methods to extend the class of dynamics for which this property holds. So we tried to look for another approach. And one motivation for the approach we ended up with is a speculation by Fish and Hofer from 2020, so even before Erie's conjecture. So this is from their paper about almost existence of periodic orbits, something like that, from 2020. They say that the Hamiltonian C-infinity closing lemma is intimately connected to the existence of sufficiently rich Gromov-Witten theory of the ambient space. So basically, this speculation, in my opinion, gives motivation to try to deduce the strong closing property directly from holomorphic curves, kind of without going through homology theories like context homology and flow homology. This approach was actually taken by two relatively recent works. So the first one was by Hutchings. And these were kind of very inspiring for us. So by Hutchings in dimension 3 and by Etmir in dimension 2. So basically what these works do, so for example, this work constructs invariants from holomorphic curves, directly from holomorphic curves that kind of mimic the behavior of invariants coming from embedded contact homology that were used by Erie in his proof of the closing lemma in dimension 3. So using these kind of direct holomorphic curve invariants, Hutchings was able to reprove a part of Erie's theorem in dimension 3. And then the work of Edmir does a similar thing for Hamiltonian diffeomorphisms in dimension 2. Okay. If you just look at the invariants constructed in these works, up to some kind of minor corrections, you can give the same definitions in higher dimensions. But then, at least for us, it wasn't clear how to compute these invariants, and in particular, how to deduce a closing property. And so what we decided to do in order to study the higher dimensional case is to take kind of a slightly different approach. So our approach basically, kind of the line of thought was as follows. Suppose you wanna study a closing property. So what you really want to understand is kind of, you don't care what was your original dynamical system, and you don't really care what's, happens in the end. You kind of want to know the difference. You want to know that as you change the system, a periodic orbit was created. And so it seems to us that it kind of makes sense to try to construct invariants that are not invariants of a dynamical system, but kind of measure the difference between two. Okay, so construct invariants measuring, let's say, change rather than invariance of a given flow or diffeomorphism. And geometrically, this change, so the change is encoded as a symplectic cobordism And I'll explain soon exactly how this works. Symplectic cobordism. Okay. Any questions so far? So before I explain kind of the construction of these invariants that measure the change, we really wanted to kind of deal with Reb flows on contact manifolds and with Hamiltonian diffeomorphisms at the same time. And so the first thing I'm going to do is to give a definition that enables us to kind of unify these two settings to a single setting. Okay. So this is unifying contact and Hamiltonian settings. Okay, so I'll give a definition. It might look, I don't know, a little bit undigestible at first, but then I'll explain how these two settings sit in it, and then hopefully it will make sense. So the definition is a conformal, stable, Hamiltonian manifold is a triple y omega theta, such that y is an odd dimensional manifold, let's say closed. Omega is a 2-form on y, sorry, 2-form y, and theta is a 1-form on y. And they satisfy the following relations. So theta is positive on the kernel of omega, and d theta is proportional to omega with the proportionality constant, we call it cy. So this proportionality constant, we call it conformality constant. And it's we demand it's non-negative. Okay? On such a kind of given such a setting, there is a natural flow on y that is induced by, let's call it Rabe vector field. So it's basically the vector field that is that spans the kernel of omega and normalized by theta of r is equal to 1. So you kind of see the similarity to the contact case. So this generates flow on y. Okay, so now let me give 2 examples, which are basically the contact and the Hamiltonian settings. So the examples. Well, the first is contact manifolds, right? So if you have a contact manifold with a contact form, then it's a conformal stable Hamiltonian manifold with omega being d alpha and theta being alpha. So in particular, in this case, the conformality constant is 1, sorry. And then the second example is if you have a closed symplectic manifold and you have a Hamiltonian diffeomorphism on it, then you can consider the mapping torus of this diffeomorphism. So it's simply the manifold you obtain by crossing M with the 0-1 interval and quotienting by gluing 0x to 1 b of x. So maybe let me draw a picture. So maybe if this is M, and here we have phi, then we can construct the mapping torus. M would sit like this. And then if you look at the flow of the partial t vector field, where t is the coordinate on the interval, so this is t, then the return map to this M slice is going to be captured by phi. Okay, so this mapping torus is also a conformal Hamiltonian manifold. So why does this work? Sorry. Okay, so Y is M phi, which is a 2n minus 1 dimensional manifold. And the 2 form omega is simply the lift of the symplectic form. So it lifts to Y, and theta is the closed form dt. So in particular, d theta is 0, which means that the conformality constant is 0. Okay. If you're familiar with stable Hamiltonian manifolds, this is kind of a subclass, a restrictive subclass of stable Hamiltonian manifolds. And if you ask yourself, why don't I work with just stable Hamiltonian manifolds? The reason is we tried hard and we didn't manage. So this conformal condition gives you some structure that kind of seemed to us like necessary for the good behavior of the invariants that we want to construct. In particular, one of the important features of this conformality condition is the fact that conformal Hamiltonian manifolds, unlike general stable Hamiltonian manifolds, have a well-defined or canonical symplectization. So let me tell you what is the symplectization. So you can always cross a manifold with R. But for general stable Hamiltonian manifolds, this product doesn't have kind of a canonical symplectic form on it. But when they are conformal, then it has, so this has a canonical symplectic form. Let's call it omega hat. You can write down a formula, but I'm gonna avoid it in general. Instead, I'll just tell you it's the unique symplectic form that, so this is kind of my picture for R cross Y. So this is the R direction and this is 0 cross Y. So it's the unique symplectic form that agrees with omega on 0 cross Y and expands in the R direction with the rate of expansion being this exactly CY thing. But I can tell you what you get in the case of contact and the contact in the Hamiltonian case. And it's basically kind of the standard symplectic forms on symplectizations. So here you get d e to the r alpha, and here you get d r theta plus omega. Okay. You can also define conformal cobordisms between conformal manifolds. Basically, the demand is that you preserve kind of this conformal structure. In particular, the ends of the cobordisms are going to have the same conformal structure CY, or you can think of it as like we're not allowing cobordisms between contact manifolds and mapping tori. I'm not gonna give a general definition just because it's kind of lengthy, but instead I'll just give a sufficient subclass that is easier to state. So conformal cobordisms. So let's just consider an example. And this is a subgraph cobordism. So suppose that you have a function from Y to R and it's taking positive values. Then you can draw the graph of F in this symplectization. I don't know, maybe something like this. So this is the graph of F. And then you can take, so this generates a cobordism X dimension 2n with omega hat, simply by taking the region between the graph and 0 cross Y. So this is a cobordism X between 0 and the graph of F. And maybe a sub-example is in the Hamiltonian case. So if you have a Hamiltonian diffeomorphism and you want to perturb it with another Hamiltonian diffeomorphism, so perturb by, now you consider phi 1 tau h composed on phi 1, then this corresponds to cobordism like this. So this would be the mapping torus of phi 1 tau h composed phi, and the 0 would be like the mapping torus of phi. And then this is the cobordism that encodes the Hamiltonian perturbation. Okay? All right, so if there aren't any questions, I can define the invariants. Sorry. Okay, so SFT spectral gaps. So in general, these are invariants of conformal cobordisms, but we're going to always imagine these subgraph cobordisms, which are a special subclass. Okay, so before I give a definition, let me kind of say one sentence that describes these invariants. So these are basically min-max, or maybe more accurately to say sup-min measurements of areas of holomorphic curves in cobordisms. So now I'm going to give kind of an approximation to the accurate definition. That it's a bit lengthy, so bear with me, and then I'll just write one sentence of what this wants to measure. Okay, so let's fix some kind of topological data of the holomorphic curves that we're going to consider. So let me explain what everything is. G is going to be a genus bound. M is number of point constraints, points that we want our curves to pass through, and it's positive. And A is a class in the relative homology of X relative to its boundary. And T is some period bound. I'll explain afterwards why it's here. Okay, so given this data, you can define an invariant depending on this data for a cobordism by taking a supremum over almost complex structures and sets of points. I'll write this down. And then you take a minimum over some curves, and you take the area of U. Okay, so let me draw a picture and explain what's what. So let's assume that this is our cobordism, X. If you're familiar with SFT, usually you consider holomorphic curves in some completion of the cobordism. So basically what we want to do is we want to make this into an open manifold by adding kind of R cross or half of R cross the top and the bottom ends. Okay, so these are kind of symplectizations of y plus and y minus. And this whole open manifold now is going to be called X hat. Okay, so here J is some compatible almost complex structure on this X hat. P is a set of M points. So let me draw them, maybe something like this. And then U is a map from a Riemann surface, punctured Riemann surface of genus up to G to this completed X. So maybe let me draw U, something like this. Oh no, right, this is U. So U has to be J-holomorphic. It has to represent the homology class A that we fixed. It has to pass through all the points. So it has to have the points in its image. And we also demand that the total, so basically we're minimizing over the area of U. So in particular, we only care about finite area holomorphic curves, and finite area holomorphic curves converge to periodic orbits of y plus and y minus at plus and minus infinity. So we demand that the total period of orbits at the top is bounded by T. Total period top end is bounded by T. So here, this is bounded by T. Okay. So now let me say one sentence about what this wants to measure. So basically, you can think of these invariants as measuring the smallest area that is required to pass through m points for arbitrary almost complex structure. Okay, so basically you give me the worst almost complex structure and the worst set of points. What is the minimal area I need in order to capture this via a holomorphic curve? Okay.
Sorry, and the picture, is it accurate? Like the part of you, strictly speaking, you're saying it represents A, which is a class in X relative to the boundary, and then in the picture you seem to allow weird things to happen outside of X. Is that?
Yeah, so X hat has the same topology as X.
Okay.
It's just like you take a neighborhood of the boundary of X and then you stretch it by R.
Yes, but what happens here with the I don't so if I start with a map U that has say boundary conditions and the boundary of X, then I'm happy. But what I see here happening, north of Y plus is U has extra topology running out of X. Is that?
Yeah, you can.
Is that allowed?
Yes, I mean, the holomorphic curves have to live in the completion, and you can make sense of the homology class. I mean, since you know that the curve converges to orbits in the periodic at the end, you can make sense of the homology of the relative homology. So you can think of it like that. Basically, outside of some compact set, this will be very close to some determined loops in a stretching of X that is, retract deformation to X.
Okay.
So
you're not technically fixing you're allowing, like intuitively speaking, you're allowing me to move where I placed Y plus and Y minus for the sake of argument.
Yes. But as a homology class, it doesn't matter. Yeah.
Sure.
Okay. Like there is a way to make sense of the homology class of the curve once you know it converges in the end, and to match it with a relative homology class of X and the boundary. Right? Thanks. Any more questions? Okay, so now I want to say a word about this T-bound, which is maybe kind of the least standard part of this definition. So the period bound is here for two reasons. The first is not interesting so much. It's just a technical compactness issue. But the second one is more interesting, and it's basically like you can think of this T parameter as a filtration of the invariants. And the filtration by t, by kind of top period that you allow, basically enables you to prove a stronger statement than just closing. It enables you to prove what we call quantitative closing statements. So in the paper by Hutchings that I mentioned earlier, he basically defines, he gives a definition of a quantitative closing measurement. Basically, it's saying like, so you can give a quantitative refinement of this closing question by saying, suppose I want an orbit of period up to 100. What is the size of perturbation I need to achieve this? So such statements can be proved in this case using these invariants due to the T filtration. Okay. And then finally, I want to say that, okay, so we defined invariants for cobordism. You can also define an invariant for conformal manifold Y. So we can define, if we have a conformal manifold, so think of it as like a Hamiltonian diffeomorphism or a contact manifold, we can define the gap of Y to be the limit over epsilon going to 0 of the gaps of a kind of thin trivial cobordism over Y. So take the interval of length epsilon, you cross it with I, this is a cobordism, right? So maybe this is a picture, and this size is epsilon. But again, this is not a spectral invariant of Y. It doesn't take values in the spectrum of Y, it takes values in the difference set. So you should still think of it as like measuring difference, right? Right, so these spectral gaps have many nice properties. I'm going to state only 3 of them so that we don't spend too much time on this. But basically, like all of the ugly analysis goes into proving these properties, and then you can just use the properties to prove stuff like this closing property. Okay, so let me give 3 properties. So the gaps satisfy. Well, the first property is Hofer continuity. So it basically says that the gaps vary continuously in X with respect to, or in Y with respect to Hofer metric on cobordisms or manifolds. So let me try to explain what this Hofer metric is. So assume this is our cobordism, and we complete it by adding these R cross the ends. Then basically, one way to understand this Hofer metric is that it corresponds to C0 metric on graphs. So I can extend or shrink this cobordism by adding or subtracting, graphs of C0 small functions, and the C0 distance here is Hofer, is what we call Hofer metric. But another way to think of it is that if you just look at the contact subclass, then this Hofer distance is just the C0 distance on contact forms. And if you look at Hamiltonian diffeomorphisms, this is the Hofer metric on diffeomorphisms. That's why I read that. All right. The second property, I don't know, let me call it monotonicity. There is like a much larger, much more general thing that holds, but I'm gonna give you kind of a very specific, easy to state statement. So basically for every sigma and t, the Gromov capacity of the cobordism bounds below the spectral gap of X. So picture is, suppose we have like a cobordism like this Hamiltonian perturbation bump thing, then the gap of this is at least the size of this ball. Okay? And then the third property is spectrality, but again in this difference sense. So G sigma t of X takes values in the spectrum up to T of Y plus minus spectrum up to T of Y minus. So here X is between Y minus and Y plus. Okay, and here these sets are basically periods of orbit sets of total period up to T. Okay, so kind of generically, you can think of this as a finite set, and then this would be another finite set, and you just take the difference. Okay? Any questions?
Sorry, yes. Why do you call monotonicity monotonicity?
Okay, that's a great question. More general statement of this is that if you have a Liouville domain that embeds into your cobordism, then you can define similar invariants for a Liouville domain, and then the invariant of the Liouville domain will be bounded by the invariant of the cobordism that contains it.
Thank you. Thank you.
Yeah, they also have monotonicity under stacking of cobordisms, one on top of the other, but I don't have time to go into that. Okay. So now I want to give you a sketch of the proof of how you use just these three properties to prove the closing, the strong closing property in some case, or like just to see that these gaps can detect the strong closing property. That's a better formulation. So application for closing. So here's the theorem. If the infimum over sigma and t of the gap y is 0, and omega represents a rational cohomology class in Y, then Y satisfies the strong closing property. Okay, before I give the sketch, let me just say about this condition. I kind of believe it's necessary. So in particular, it fails for Raman's counterexample. It holds trivially for Hamiltonian diffeomorphisms in dimension 2, and it holds trivially for contact manifolds. Okay. So now let me give the sketch of how to show this. Well, basically, the idea is we want to prove this strong closing property. So we need to take kind of any bump, any deformation. And we want to show that as we raise it, a periodic orbit is created. So let's write this in the language of these cobordisms. So we have 0 cross y. This is R. And then we have a graph of tau h. And we can call this subgraph cobordism x tau. So we have kind of a continuous family of cobordisms, x tau. Okay. So the first thing we can notice is that at time equals 0, we get basically kind of, you should take like an epsilon and limit and so on. But basically what you get is the gap of y. And we assume that the infimum over all data is 0. So let me write it as there exists sigma and t such that this is as close to 0 as I want. Okay, on the other hand, the monotonicity property tells me that at time 1, this is positive and depends only on h. So depends on h, but h is fixed. So it's kind of the size of the subgraph of x. Okay. And then finally, so basically these two observations already tell me that my gap cannot stay the same when I do this deformation. So it cannot be that x tau is constant in tau. The gap of x tau is constant in tau. But on the other hand, if no orbits are created, you can use the continuity and spectrality and this rationality condition. So it goes in here to show that that if there are no orbits, okay, so if there are no orbits that are created by this deformation, then basically the spectrum will stay the same. And then these two together will tell you that the map tau goes to G of x tau takes values in a measure 0 set, and if it's continuous, it has to be constant. So from this, you could conclude that G x tau is the same for all tau. Okay, so this gives you a contradiction. This argument is very similar to, just with different invariants, to what Erie did and what basically all of the works I know on closing lemma did. Okay. Any questions about that? Okay, so if there aren't any questions, maybe I can say a few words about how you use Gromov-Witten invariants to compute these gaps. So that's kind of the hard part of, or one of the hard parts. The argument is not difficult. It's just that doing this in wider generality than we did, it's currently I don't see how to do that. Okay, so basically this theorem tells us that if we want to show a closing property, we need to prove that for the manifolds we care about, the gaps are arbitrarily small, right? So the question is for which y can we show that the infimum of gaps is 0. So one idea, okay, or maybe before I say the idea, let me say what the difficulty is. So these gaps are defined as a supremum over almost complex structure. So in particular, in order to give an upper bound for the spectral gap, you need to know existence of some small area holomorphic curve for any almost complex structure, okay? So one idea to do this, of how to do this, is embed y into a closed manifold. So maybe y is 2n minus 1 dimensional, and we want to embed it into a closed, whoa, sorry about that. I don't know what happened. Sorry. So we want to embed it into a closed manifold. of dimension 2n and use Gromov-Witten invariants to get existence of curves, so to produce curves in this very thin cobordism. Okay, so now let me show you how this can be done on the simplest example that we know. So this example is kind of not interesting from the point of view of closing, but it captures most of the essential ideas, I feel, for the general case. So suppose that your manifold Y, the flow on it, generates, so the flow on Y generates a free S1 action. So this is sometimes called ZOL. So basically in this case, Y is going to be an S1 bundle over the orbit space, which is just a quotient. So it's Y over the S1 action. So let me draw a picture. So suppose this is this base B. Over each point here, I have a circle. So this is S1. And then Y is, forgive me for the weird picture, but Y is kind of the S1, right? So it's like S1 over each point. I hope this makes sense. So the idea is basically that you can complete this S1 bundle into an S2 bundle. So picture is like we can create an S2 bundle in which in which Y sits. So this is going to be M of dimension 2n. So let me write it down so we can complete. It will basically be a quotient of the complex line bundle completion of the S1 bundle. So we can complete Y to an S2 bundle. Let's call it M omega, and it's of dimension 2. No, maybe I want capital omega. And it's over B. Okay? And now the idea is that this thin cobordism over Y, it embeds into this closed manifold whenever the area of the fiber is at least something like epsilon. So omega of S2 times point, which is kind of the fiber. So maybe let me say fiber is at least epsilon. Okay, so maybe now the picture is this. So this would be minus epsilon times Y, 0 times Y. Okay, does this make sense? And then the idea is that if you know that you have closed holomorphic curves in the homology class of the fiber, you can kind of break them to get holomorphic curves in the cobordism. So let me try to write it down. So a lemma says that suppose Gromov-Witten invariants of some topological data sigma prime, which is related to the sigma that you want to compute the gap for, of M with the homology class of the fiber S2 times point. Suppose this is not zero. So Gromov-Witten invariants are, I should say, are basically counts of, roughly speaking, they're counts of holomorphic curves in a given homology class, and they are independent of J. So this would tell you that for a generic J, there exists a closed holomorphic curve in the class of the fiber, right? So if you know this, then you can basically break this closed holomorphic curve into a holomorphic curve in the cobordism and show that the gap of sigma with some T naught of this thin cobordism is bounded by the area of the fiber, which is the area of the original closed holomorphic curve that you had. So let me try to draw this. So suppose this was your holomorphic curve, then you can kind of break it and take this piece, roughly speaking. The area will be obviously bounded by the area of the total thing. And you can use this existence to give a bound on the gap. Okay. Any questions?
So, excuse me, Shira, in your proof on the page before, if you can go just, it's maybe you have the second point that says that G sigma tau of x1, I think,
Yeah.
is bigger than 0. So maybe I didn't catch why is that true?
Oh, yeah. So thank you for asking. So basically we had the property, scroll more back. So we had this property.
I see the monotonicity. I understand. All right. Okay.
Yeah, thank you. I should have wrote it down.
Okay, because I mean the whole thing is for this invariance not to become all 0.
Yeah. It's also kind of not trivial to show that they're not all infinity, or many of them are infinity.
Yeah, right. Okay, great. Thank you very much.
Extremal. Yeah, so I think in a sense this property really tells you that it captures some sort of size of the cobordism. And therefore it's interesting to understand in what generality the size of a 0 cobordism is 0.
Yeah, sure. Okay, great. Thank you very much.
Yeah. Okay, I think I can stop here. It's almost time anyway.
Okay, well, thank you very much. Any questions for Shira? Yes, please.
Okay, is it me?
Yes, please.
Yeah, thanks. So thanks for the nice talk. So you mentioned first that kind of this idea that, well, that non-vanishing of Gromov-Witten invariants kind of implies this strong closing is speculated by Hofer and Fish. So do you think that, so how does kind of these, the last point that you've shown here, this relates to kind of their conjecture? Do you think like this is what they have?
Yeah. Yes, thank you so much for this question. So basically, we wrote a criterion. I can write it down. It's not extremely pretty, but you can write down a criterion in Gromov-Witten theory. So basically, if there exist manifolds, homology classes, genuses satisfying some Gromov-Witten invariants non-vanishing, then you can conclude closing lemma. So through these invariants, you can make this formal. Like if I know non-vanishing of some Gromov-Witten invariants, I can produce closing lemmas. We showed this closing lemma for a very restrictive class of flows, still extending kind of previous works, but it's really far from, everything. You can't expect to have actually everything, but I believe it's far from everything that's true even. And in a sense, the difficulty is we don't know existence of holomorphic curves. So if I knew more Gromov invariants were non-vanishing, that would help me.
Okay, yeah, thank you. Thanks.
Do you get more information if you know the value of the Gromov invariance, or is it the only thing you care is the vanishing?
Oh, the only thing I care is the vanishing, because I do just min max over the areas.
Yeah.
So I don't care if I have many. I don't care if I have several curves in the same class. They would still give me the same contribution for the min max invariant, because the area is just determined by the homology class. What does matter is naturally like the dimension of the moduli space. So one thing that is kind of seen by this work, I think people like Michael Hutchings definitely, and other people understood it earlier, but it's kind of, you can see where the difficulty between the low dimension and the higher dimension lies. Basically, and it's more apparent when you do this kind of a direct holomorphic curve approach, because you can see, for example, in CP2, the dimension of the moduli space of holomorphic curves of area A is much bigger than in CP3. So it goes quadratically in the area. The dimension of the moduli space goes quadratically in the area in CP2 and linearly in the area in CPN for higher n. And this is exactly what makes it harder for you to produce low area holomorphic curves, which are what we need in order to use these gaps to prove the closing. So I think kind of a nice side effect of this approach is that you see exactly what is important in the low dimension case.
Interesting. Thank you.
Can I ask a
More
question?
questions.
Can you go back to the page of the proof where Octave was asking questions?
This?
So just, yes, right there. So here Y is dimension 2n minus 2, right?
Y is 2n minus 1.
2n minus 1, sorry, right. Can you comment, maybe I missed it, can you comment on the rationality of the homology class? Actually, what is omega? Omega is the, so what is omega actually?
So omega is in the context case, it's d alpha, and so it will represent 0 class. In the Hamiltonian case, it's the lift of the omega in the closed symplectic form to the mapping tori, to the mapping torus. Okay. So if you had a Hamiltonian diffeomorphism on a rational symplectic manifold, this would be satisfied.
Yes.
And if not, then not. And also you can do the same thing so I didn't say it, but you can take a mapping torus of a symplectomorphism, not a Hamiltonian diffeomorphism. Yes. And then this captures like also the irrationality of the symplectomorphism.
I see. Right.
Okay. So you can think of Hermann's example in two ways, like either an irrational symplectomorphism or on a rational manifold, or a Hamiltonian diffeomorphism on an irrational manifold. And in both cases, this omega will be irrational.
Okay, but Hermann's counterexample, I mean, one way to think of it is a hypersurface inside, it's like this, you could think of it as a hypersurface inside some symplectic manifold, right? So yeah. I want to take Y to be that hypersurface. Is it then?
You can't, it's not conformal. If you wanted, okay, so you can think
that's exactly what I was going to ask, actually.
Yeah,
so if you take Y to be one of these hypersurfaces in his counterexample, is it even a stable? Forget conformal. It's probably not even a stable Hamiltonian structure, right? Or you know?
I'm not sure about stable actually. It's not easy for me to see it's not stable because the dynamics is stable.
That's what he proves. Okay, but yeah. It certainly is not conformal stable, so it doesn't fall into this. So is it covered by your theorem for getting the cube?
Let me think. I mean, the rationality would still be a problem, no?
Right,
Because you
I'm
would
saying,
say-
so forget the Q,
No. When I said, okay, I think I understand the confusion. When I said this fails for Riemann, you can think of Riemann's counterexample as a counterexample for Hamiltonian diffeomorphisms, not for a hypersurface.
okay,
And then you see that this is the problem. So you
I
can,
see.
his counterexample also gives you, you can think of it as like this
Yes,
weird
okay.
hypersurface. That's true. But you can also think of it as like, it gives you a weird Hamiltonian diffeomorphism that has a whole neighborhood in which you cannot produce closing.
Right, okay, got it. So,
Yeah.
okay, and can you say, so where is Q used in the proof?
Yeah,
You're saying-
here. So basically, the kind of the value set. So, here I think I omitted something. This should be like together with areas. Okay, so maybe here I should say something more accurate. Let me say that. So this is true in the contact case, but generally, this takes values in kind of the different set plus the areas that are captured in Y. And that's why the rationality, like if this is irrational, this set is big.
Yes, got
So
it.
maybe a better way to say it is like area spectrum up to T of the cobordism, and that amounts to difference of the spectra plus this the areas of the
Oh, I see,
second
I see. I see.
Yeah.
This might be-
spectrum minus spectrum plus that kind of H2, area of H2.
Okay, got it. Thanks.
So basically you see that the set is too big if it's not rational.
Yes.
Like in the proof, it's funny. It looks like a little bit like a technical thing, but
Okay. Thank you.
but then the fact it does not hold for Riemann makes it seem more relevant. I don't know.
I mean, Hermann's counterexample is also one of these places where there are no Gromov-Witten invariants. So it could be that it fails for that reason. So it seems to fail. I mean, yeah, it's on a torus. So, well, I guess you maybe hope for a higher genus. There are no holomorphic spheres, right?
Yeah.
So
Yeah,
maybe maybe it fails for that reason.
but I mean, somehow in low dimensions, you don't care about, in lower dimensions, you don't care about the topology of the manifold. Because, I mean, yes, your homomorphic curves that are going to save you are going to be of higher genus.
Right. Yeah.
Yeah.
Okay.
Also, kind of roughly speaking, the gaps ask less than closed holomorphic curves, right?
Sorry?
I'm saying, roughly speaking, these spectral gaps, invariants on cobordisms, they ask less than closed holomorphic curves. Like you only need a piece. So for example, I didn't mention, but you can prove, in some cases, you can prove this bound without Gromov-Witten theory, just kind of by hand working inside the cobordism. But then, at least for us, with our technical abilities, we needed some simplifying assumptions to do that.
I see.
You could still do some kind of cobordism argument, saying like, I start with a nice almost complex structure, I know where the homomorphic curves are, and then I deform, and then I try to show that existence still survives. Or
I see.
Yeah. So we managed to do it under some simplified assumptions, but yeah.
Thank you.
Any more questions? Well, maybe let's thank Shira for now.